Hello. Going into the chemical bonding unit, we're going to kind of go over the basics of what chemical bonding is. The first thing we want to kind of tackle is called intramolecular forces. They're physical forces that hold atoms together in a bond, a chemical bond, that maintains the integrity of the compounds and molecules. So these forces, these pulls and pushes between atoms is what allows them to kind of stick close to each other to maintain the physical and chemical properties that compounds and molecules have. The magnitude of the force does depend on a couple of factors. The types of atoms that are in the bond, so the reactivity of those atoms, the electrons of those atoms, so on and so forth. The size of the atoms can be a huge thing too. If you have too big of an atom, the bonds may be really long, which may not hold the integrity. If they're really short, they may be hard to pull apart, and so on and so forth. The number of electrons being used in the bonds, which we'll dive later into further videos. But a couple of types of chemical bonds that you'll come to see throughout this unit. One's called ionic bonds. It's a chemical bond created by the stealing of electrons from one atom to another. I call it the bullying bond. Let me say that again, the bullying bond. So it's when an atom really goes over, kicks another atom and says, give me your electrons, and then those electrons are stolen. And this happens between ions because of ionic bonding. It typically occurs between a metal and a nonmetal. The reason why is because metals form cations and nonmetals form anions. And due to the difference in charge, they want to form an ionic bond. Covalent bonds is when a chemical bond is shared was created by the sharing of electrons between two atoms. I call it the best friend bond. So your best friends want to share everything. And so even though a lot of you are alike, which makes it non-metal atom bondings, so even though they form similar charges, they want to share electrons. And this sharing of electrons allows, even though they have similar charges, the constant flow allows the charge to kind of fluctuate and allows them to stay together. So covalent bonds are the sharing of electrons. Ionic bonds is the stealing of electrons from one atom to another. There are two different subtypes of covalent bonds too. There's called polar covalent bonds and there's non-polar covalent bonds. And we'll get into what polarity means here in just a little bit. But the types of bonds are determined by a difference in electronegativity between the bonding atoms. So the difference between polar and non-polar covalent bonds and ionic bonds is a difference in the electronegativity of particular atoms. In regards to that, the way it breaks down is that the greater the electronegativity difference, the more ionic it is, and the lower the electronegativity difference, the more non-polar covalent it is. So if you have an electronegativity difference of 0.5 or less, then it's non-polar covalent. And you see a lot of this with diatomic molecules because the atoms have the exact same electronegativity. So the bromine molecules, the chlorine molecules, the iodine molecules, so on and so forth. Polar covalent is something you'll start seeing with a lot more common elements like oxygen and chlorine and stuff like that. So water has two OH bonds, and so they're polar covalent. So water is a polar molecule because it has two polar covalent bonds within it. And this is a difference between 0.5 and 1.7. Ionic is anything greater than 1.7. So the further you are on the left-hand side of the periodic table compared to the right side, the more ionic it becomes. So that's your salts like sodium chloride, magnesium bromide, strontium oxide. Those metals and nonmetals is where the greatest electronegativity difference is. So you can actually look at it with a chart like this. So for example, hydrogen has a 2.2 electronegativity compared to the 3.4 that oxygen has. So it's just right in where that polar covalent is. But if you look at sodium, it has less than 1 electronegativity. And again, this is following the trend of electronegativity because electronegativity goes up as you go up the periodic table, but it increases as you go from left to right. So the most electronegative element is fluorine. So there's a huge difference between, hydrogen and fluorine and sodium and fluorine there, so that makes it ionic. So a lot of the cations that you see, since they have very low electronegativity, they're more likely to form ionic bonds because fluorine will go over and say, okay, sodium, I want your electrons, and sodium will just give its electrons away to fluorine so it could become octet, but then sodium's like, well, I'm just going to be octet on my own because now I can represent neon, and so on and so forth. So polarity. Polarity is a physical property of compounds in which bonding atoms create an uneven distribution of charge across a bond. So that means that atoms become more partially positive or negative by how their electrons are shared or taken away. The difference in charge creates what's called a dipole moment. Di meaning two, pole meaning just an origin of charge, I guess is the best way to say it. So you can kind of think of it like planet Earth has two, the North Pole and South Pole, and there's a magnetic field around the Earth, and that's due to also a difference in charge, and that difference in charge allows that magnetic field to occur. These dipole moments demonstrate an atom's tendency to become attracted to electrons. So atoms with higher electronegativities are more likely to form negative charges because their dipoles are more likely to be attracted to positively charged ions. So the more electronegative you are, the more electrons you want to suck in, which more partially negative charge or to form negative ions that you want. Based on this charge, they're more likely to draw in positive charges to kind of equal that out a little bit. Polar molecules have created dipoles. Nonpolar molecules do not have dipoles, or they have very low-powered dipoles. So nonpolar molecules can have dipole moments, but they have to be very, very small in magnitude to where, a dipole moment only may occur depending on what that molecule or compound comes in contact with. But if it's by itself, then it pretty much doesn't have a dipole at all. So let's take a look at a water molecule. So have oxygen, hydrogen, hydrogen. Now, oxygen and hydrogen are bonded to each other. Now, we know based off the last slide that the electronegativity difference is in between the 0.5 and 1.7 mark. But how does that dipole move? Well, the thing is, with the electronegativity of oxygen being 3.44 and electronegativity of hydrogen being 2.2, we know that electrons want to go towards the most electronegative element. So this bond right here, which represents electrons being shared, the electrons are more likely to flow in and around the oxygen for both bonds. So the dipole moment moves towards the oxygen here. So we know that the flow of electrons is more likely to go towards the oxygen atom, which makes oxygen more partially negative and hydrogen more partially positive. So kind of getting into chemistry terms in regards to just chemical bonding in itself, is compounds, which we know a little bit about already. Pure substances are composed of two or more elements that are chemically combined. There are two types of compounds. There are salts. It's a compound that's formed between two or more metal and non-metal elements being attracted via opposite charges. So it's pretty much a metal and a non-metal being bonded together with ionic bonds. So salts are anything that has ionic bonds within it. A bond associated with salts is ionic bond between metals and non-metals. A molecule is a compound that's formed of two or more non-metal elements sharing electrons, which means that molecules are with covalent bonds. So your organic molecules, when I say organic molecules, it's carbon, hydrogen, nitrogen, oxygen, all bonded together in covalent bonds. Chemical formulas, they're used to represent the composition of a substance using chemical symbols and numerical subscripts, which a lot of you already may know is that, H2O is water, but water is composed of two hydrogens and one oxygen. So the subscripts demonstrate the number of atoms or groups of atoms present within a compound. So a subscript can represent one particular element or atoms of an element, or it can represent a group of elements together. So if we look at H2O, we know that the 2 on the H means that there's two hydrogen atoms within that molecule. Oxygen has this invisible 1 here. In chemical formulas, you don't have to put a 1. It's just assumed that there's 1 since the element symbol's there. But anything greater than 1, you actually have to put a subscript there. So we know that it has 2 hydrogen atoms and 1 oxygen atom. Then we look at sulfuric acid. It has 2 hydrogen atoms, and then there's an invisible 1 here next to the sulfur. And then there's a 4 next to the oxygen. So there's 4 oxygen atoms, 2 hydrogen atoms, and 1 sulfur atom. And then again, we look at this. This is an ionic compound, so it's calcium and what's called hydroxide, which we'll learn later on. Hydroxide is within this bracket here, and this 2 is on the outside. So this 2 means that's 2 times whatever subscripts are in here. And since there's no subscript, we can assume that there's each 1. So 2 times 1 is 2, 2 times 1 is 2. So it turns out that hydrogen does have 2 atoms within it, because there's 2 hydroxides attached to this calcium. There's 2 oxygens in it, and then there's only 1 calcium. So then there's chemical equations. It's an accumulation of chemical formulas that demonstrate a chemical reaction by the rearrangement of atoms or groups of atoms. So you take a series of compounds, you put them together. We know based off the law of conservation of matter or mass and energy that the matter can't be destroyed. It can only be rearranged. So these chemical equations represent what goes on in a chemical reaction itself. The group of formulas to the left of the arrow are what's called the reactants, stuff that react together. The group of formulas to the right of the arrow is what's called the products, so that's what's produced in the reaction. And then sometimes that you'll find there's an arrow in the chemical equation. Sometimes above the arrow you'll see letters or other chemical formulas on there, and what it is that's conditioned. So it's what you're using in the reaction to make the reaction occur in general. So a common example is that this is photosynthesis. So you take glucose, which is sugar, plus oxygen, and then it produces carbon dioxide and water. It can also be reversed. So what we do is with plants is that we give plants water, we breathe out carbon dioxide, and they take in that to produce sugar for their molecular processes, and they breathe out oxygen, which we breathe in. And this has all occurred with this is H nu, which represents light. So that's the reason why plants have to have light, because light is a catalyst to allow this reaction to occur. So that's all for this video. If you have any questions in regards to this stuff, please come talk to me, because if you're not getting this, then this unit's going to be kind of hard for you. So please come talk to me, email me, whatever you need to do. Otherwise, thanks for watching this video, and I hope to see you in the next one and see you in class. Bye.